One of the things I've been meaning to do for some time is to build up a software-defined radio using the Raspberry Pi, as I did earlier with the Pi board and bare metal programming. So in order to do that, I need to find out first how to drive peripherals from the Pi using its GPIO pins. I thought I'd share some of those learnings. I thought people might be interested in that. They're doing their own experimentation with the Pi. And one of the things I really want to get to with the Pi is learning how to drive I2S out of the Pi. There are I2S pins there, obviously in order to build a software-defined radio, you need some mechanism to audio signal processing. So the video I'm putting together here, some of the things that I'll go through are, firstly, what GPIO capabilities exist on the Pi and how they differ from, let's say, the STM stuff that I've been doing earlier. What C and C++ libraries exist to access the GPIO pins. And then I've got some specific nuts and bolts examples for GPIO input and output, serial or UART access, SPI, I2C, and we'll see where we go. What I won't get to in this video is kind of my ultimate goal, which is to do some audio processing, as I did, as I mentioned earlier, for the Pi board. On the Pi, there are alternatives actually to I2S. So obviously I could use the I2S pins that are on the Pi. Alternatively, I can just use, for example, a USB hub that has audio in and audio out, something like that little box on the in the middle right there. So definitely some other choices I've got with the Pi here. A couple of notes on this Pi here. This is a Pi 4 with 2 gigs of RAM running Raspberry Pi OS. I've also tried this on a Pi 4 with 8 gigs of RAM running Ubuntu. Pretty much the techniques are identical. They differ primarily in how you permission the devices that you talk to program the peripherals. So, but yeah, the code is identical between the two platforms. Okay, so let's spend a bit of time going over the various GPIO pins that exist on the Pi, and here's the kind of standard 40-pin header that's been used in the Pi for some time, and this is kind of the outside of the Pi here. So pin 1 is, and let's just pan up to the Pi itself. So pin 1 starts on the inside here. So it goes pin 1, 2, 3, 4, and so on and so forth. Now, interestingly, the GPIO numbers themselves don't correspond in any way to the header pin numbers. So you can see here, GPIO 18 is pin 12, and there's no real relationship between the GPIO number and the actual header pin number. So just going through some of the capabilities, all the GPIO pins on the Pi are 3.3 volt tolerant. And unlike the STM microcontroller, they are not 5 volt tolerant, so you definitely want to keep 5 volts away from any of the input pins here. The processor itself is an ARM A72 based processor, so it's similar to the STMs in that they're both ARM architecture, but the Pi is based, or at least the Pi 4 is based on a BCM2711, and I'll include a datasheet to that microcontroller. I mean, obviously the datasheet contains all the information on how you go about programming the peripherals, which we'll get to shortly. So quickly going through the header here. So we've got at the top here, we've got a 3.3 volt power rail. We've got a couple of 5 volt power rails here, and there's 3 or 4 ground pins as also. There's one here, there's one here. Well, actually, there's more than 3 or 4. So as you can see, all the other pins on here are GPIO pins, and you can use any one of them for general purpose input output. And then some of them have special purposes. So you can see, let's just walk through some of the special purpose ones. So you can see up the top here, we've got SDA and SCL. So these are the I2C pins. You can also do SPI programming. So here's the MOSI MISO, the clock, and this is the chip select register, and you've got a chip select pin, and you've got 2 available here. You've got PWM also, and that's pins 12 and 13. So we've got this pin here, and Sorry, no, that's not. It's GPIO 12. There we go. Not header pin 12. So GPIO 12 and GPIO 13 are PWM. We have the I2S pins that I mentioned before, and they're down the bottom here. So where we have this pin here, pin 19. We've got pin 18, which appears up here. Then we've got pins 20 and 21, PCM. So here's data in and data out for the I2S. We have a UART interface here, and we'll get to the UART here. So we have the transmit and receive UART pins. And then finally, something I won't get to is this pin here, which is a timer pin. Interestingly, on the BCM2711, there's no ADCs or DAC here. So if you want to do analog to digital, digital analog, you have to use external circuitry. And I've actually got an example using an ADS1115 and how you would integrate with that. Okay, so the next question is, how do we access these GPIO pins? So obviously it's a Pi, it's running Raspberry Pi OS. We're not going to be doing bare metal programming here, although we could certainly. But let's assume we want to continue using some variety of Linux, and how would we access them? So there's at least 4 different ways of accessing GPIO from a Pi. So I've got them up here. There's sort of 2 that are together, and that's memory access plus mmap. So basically that involves opening up the either dev mem or dev GPIO mem, doing a memory map, and then effectively accessing the registers as if it were bare metal programming. Now you are going through through those devices and through those drivers, so it's not as fast as bare metal programming, but it looks exactly like bare metal programming. Now some of the differences from bare metal programming is, well, one of the primary differences is you don't have any interrupt processing, so you can't sort of register an interrupt on a button press and then get a callback when that button gets pressed. Now, there are techniques to do that, which I'll be walking through some of them, but that's one of the primary differences. Also, you can't use DMA as well here. So that does present a bit of a challenge if I wanted to do some I2S programming down the track. And obviously, I think at that point, I'd probably have to either write some kind of kernel driver or something like that to access the I2C and do DMA or interrupt programming. So the second technique is to use the specific GPIO device and to use the ioctal or IO control calls, and that's at dev GPIO chip 0. Oh, before I move on, both dev mem and dev GPIO mem require privileged access. So dev mem requires root, pretty much. There are some techniques that you can permission it with capsys and so on, but really it's no different to having to require root. So you'll see it as I get through that. I'm running these GPIO programs with sudo. Dev GPIO mem is a bit different. It is more restricted. It just gives you access to programming GPIO. Doesn't give you access to I2C or SPI, but it requires lesser permissions to access. So the next one, I just talked about that GPIO device plus IO control, again /dev/GPIO chip 0. That does not require root, but it does again require permissions. And then the final approach, or at least the final approach I'm aware of, is to use a specific peripheral device and use IO control there as well. So if you have a look through the dev tree, you will see there's one for I2C, there's one for SPI. On certain machines, there's one for I2S as well. So they're the basic 3 mechanisms. Now, what I'll be doing, at least in this video, is the top mechanism. So accessing dev mem, that to me looks the most like bare metal programming, which is kind of the direction I want to head here. There's nothing wrong with the other mechanisms, and in fact they're superior in some ways because they don't require super privileged access. But accessing dev mem using sudo is kind of the closest to bare metal that I can get, and so that's the mechanism that we'll be using here. So I should cover the final way that you can access GPIO is to use one of the libraries that's out there. So there's a variety of choices out there. The ones that I've been doing the most playing around with are two libraries. One's called WiringPi and the other one's called BCM2835. The first one, WiringPi, unfortunately is deprecated now, and I'll include a link to all this libraries and information. So WiringPi is actually deprecated. There is a copy repository out there, but BCM2835, on the other hand, that is actually a library that's provided as part of a book that I've been reading on it called, I think it's called Internet of Things. I'll include a link to this, but it's Internet of Things with Raspberry Pi. And that is something that the author has provided. And then finally, there are libraries available for Python. The one I have seen and used a little bit of is called rpi.gpio. And I won't be using Python here. I'll be using C in this case, but that would be an interesting one to check out for the Python aficionados. So that's pretty much on the libraries. I'm sure this isn't exhaustive. I'm sure there are piles of other libraries out there that access this. But what I'll do is, as I go through these examples, I'll start with just some bare bones access without using the libraries, just to show the flavor of how you actually access the devices, the sort of permissions you've got to have, how you access the different registers involved. And then for the follow-on, for the SPI and I2C examples that I have later on, I'll be using the BCM2835 library to access. And then finally, I do have an example that I will cover on how you go about accessing the UART. And the UART itself is just exposed as a serial device to Linux. So you can access and program that as a standard serial device. So anyway, let's move on now, and we'll do the canonical Blink program, and that's where we'll start looking at what you have to do. Okay, so let's dive straight into the code here. I am using Visual Studio Code here, and I'll provide a link to the GitHub repo that I've got this code all up at. So as I mentioned, I'll be using the mechanism of opening up the dev.mem device and mapping that into the address space of the program, and then hitting the registers directly. So you can see they're pretty straightforward open there on dev.mem. I then use mmap to map that into the address space of the user process, and I start at this magic number here, FE 200,000 hex. And what that corresponds to, if we just flip over to the manual, is that actually corresponds to the start of the GPIO peripherals. Now the manual here says 7E, but it actually maps to FE from Linux's perspective. So let's just get back to the code for a moment. So I've opened up, basically after this, map points to the start of the peripheral registers. So at that point, I'm able to poke directly into those peripheral registers, assuming the open and the mmap succeeds, of course. Okay, so now that map is pointing directly at the start of the GPIO registers, I can now start to poke some values into it. And the first thing I do is basically get the address of the function select for the GPIO pins. So just moving back to the documentation for a quick moment, you can see here the function select registers determine what the function of the IO pin is. So if we go there, you can see that in this function select register, and there's a portion of this register for each of the GPIO pins. So there's 3 bits of information for each GPIO pin, and there's something like 54 different GPIO pins. But you can see here, if you set those 3 bits to 0, it configures it as an input, which is the default behavior. If you set it to 001, it's an output. And then the remaining bits are there for specifying the alternate function. So an alternate function would be, I want this GPIO pin to act as I2C or I2S or what have you. So moving back to the code, we can see that I'm getting, because this is pin 18 I want, the function select register for GPIO pin 18 is actually the second one, or GPF select one. So I basically, PADRA is basically the start of the peripherals plus the location of the GPF select one register. So once I have that address, PADRA, now I can figure out, all right, where is pin 18, which is the pin I want to use here. Where is that in that function select register? And so that's what this piece of sort of magic is doing here. So basically, I take the location of the pin, so 18 in this case, I subtract 10 from it, because that's the sort of starting offset. And then I multiply by 3. The 3 here is the 3 bits for each of the values. And then I have 001, as I mentioned before. That's configuring the pin as an output pin. And then the mask just ensures that I'm setting those 3 bits in there. So effectively, what this piece of code here does is it figures out where in the register those 3 bits are and only selects those 3 bits. So it first masks off all the other bits to make sure we're not changing them, and then it ORs that with the value that we want to set. So the end result is 001 will be written into just the 3 bits that correspond to the pin 18 in this case. That configures pin 18, GPIO pin 18 as output. And then we move on to 2 other magic values here, 1C and 28. And let's go back to the manual here, and we can see what they mean. So 1C up here is the set register. So basically, with this register, if you write a 1 into that into a bit in this register, it will set the corresponding GPIO pin high. And then similarly, 28 is the clear register. So if you set a 1 into a pin in this register, it will set the corresponding GPIO pin low. So that's basically what we're doing here. Is I'm getting the address of the set register, and I'm getting the address of the clear register. And then down here, I'm just basically poking I'm setting that value to a 1. So here's the clear register here. PADRA 1 is the set register. PADRA 2 is the clear register. And then, as you can see, I'm just going through a for loop, delaying for 1,000 milliseconds, and then clearing the pin. So a little bit convoluted with magic values, but really pretty straightforward. I mean, obviously, this is just GPIO off and on, so you would expect it to be pretty straightforward. As we move on to SPI and I2C programming, you'll see it gets more complicated rather quickly. But that's the basic mechanism that's common across all the pin accesses. Open up DevMem, starting at the base of the peripheral registers, and then you're basically bit twiddling those peripheral registers. And this is why this is very similar to kind of what you do in bare metal programming. And obviously with the STM programming that I've done before, you have the HAL library there that's taking care of all that for you. And you're generally not bit twiddling, unless that's something that you have a special desire to do. But as we go on, I'll show you the 2 libraries that, they do a good job of abstracting you from this bit twiddling. So you've been seeing this basically in action before, but that's the result of the code. Basically, is to flash the LED on, wait a second, and then turn it off again, and wait a second, and so on and so forth. So that's I guess the canonical blink program. What we'll do now is move on to simple input processing for GPIO pins, so that'll be coming right up. Before we dive into the code, just a quick note on the electrical setup here, and it's pretty straightforward. But so I've got 2 setups, and I'm going to go walk through. One is this LED that you can see here, and that's coming off GPIO pin 18, header pin 12. and very straightforward here. It runs from the pin through the LED and then through a 270 ohm current limiting resistor to ground. So for the button that I'm going to set up, I'm going to set that up on GPIO 17, which is header pin 11. And again, that's going to be pulled straight to ground when the button is pressed. So obviously with the button, I'm going to have a pull-up configured in here so that when the button isn't pressed, the GPIO pin reads high. But I'll basically walk through how that gets set up. So let's move into the code now. Let's move on to processing and input GPIO now. And so to do that, I've got this simple little switch set up here. And I've got one side of the switch set to ground, and the other one goes all the way back to header pin 11 or GPIO pin 17. So let's check out the code for that. So here we are in the code, and so obviously the starter is exactly the same. Open up devmem and then map it as we did before for the output pin. The function select register, we're looking at pin 17 here, so it's actually the same function select register as GPIO pin 18. In this case, however, because we want this as an input pin, we configure that right here. So the value is 0 for an input pin, and then we do the same bit twiddling as before to make sure we leave all the other values as they are and only set 30 bits into the position for this pin, which happens to be pin 17. However, because I've got no pull-up resistor, external pull-up resistor on this switch, I need to configure the internal pull-up resistor appropriately here. And that's achieved by this register right here. So E8, let's just move to the documentation so we can see that. Bear with me. I'm just going to scroll up to that point of the documentation. Forgive me, I should have this prepared a little bit better. So you can see here we have these pull-up, pull-down registers right here, and there are 2 bits for each GPIO pin, and you can configure it as either no resistor selected, or alternatively a pull-up resistor is selected or a pull-down resistor is selected. So you would have the pull-up resistor if the other side of the switch went to ground, and you would have a pull-down resistor if the other side of the switch went to a voltage rail. And then 3 is reserved for some other functionality. So that's the difference in this case, is now I have to configure the pull-up, pull-down register to the appropriate value. And the appropriate value in this case is 1 to indicate I want to have a pull-up resistor configured on this GPIO pin. And then the final piece of the puzzle is, well, where's the register that is the actual value of that pin itself? And that's GPIO 0. So just going back to the document again, forgive me for sort of going backwards and forwards here in this document. Bear with me, I'm going to have to go back to the beginning of the document again. Like I said, I'll include a link to this essential document here as the general purpose I/O here. And then GPIO 0 right here is the actual value of the pin, whether it's high or low. And that's so there's obviously 2 registers there to cover the 54 possible GPIO pins, and we want the 17th bit in GPIO 0 register, which is this one right here. So let's move back to the code here. And then the final thing is, this is a typical while loop that you will have seen in the bare metal programming that just iterates through here and basically interrogates the value of this button here and prints it out. So I've already compiled that, and then to run it, which I didn't actually show before, but to run it, you, as I mentioned, all of these require root access, at least /devmem access requires root access. And let me just run that off there. and then you can see it starts out at a value of 1, pressing the button. So it goes to 0 when I press it, and then 1 when I release it. So for the next couple of examples I'm going to do, I'm going to be using the BCM2835 library that is an accompaniment for this book here. I'm not affiliated in any way with this book at all, but I thought I'd give it a plug because I think it's a good resource for learning how to program GPIO on the Pi. Again, I bought this with my own money, so I'm not getting anything free here. So anyway, let's move on to the next couple of examples. I'm going to do an I2C example or an I2C example, and then follow that up with an SPI example. Moving along with some I2C programming. The I2C device I've chosen is this ADS1115, which is an ADC. And here's the kind of electrical connections here. So the ADS1115 accepts either 5 volts or 3.3 volts. Obviously, I want to use 3.3 volts here. There's a ground connection. There is an address connection here, and the address connection determines what I2C address this lives on. So when it's connected to ground, it's addressed at 48 hex. SCL and SDA go to GPIO pins 3 and 2 respectively, and you can see those connections right there. And then just as a source for the ADC, I've chosen to just put a pot against 3.3 volts here, and then this will be an analog voltage here at wherever the pot's at, and I'm reading that through A0. So circuit's pretty simple. We'll move on to the code. Okay, so as I mentioned, for the I2C and the SPI examples, I'll be using this BCM2835 library, linked below. BCM2835, incidentally, is the predecessor to the BCM2711, which is the microprocessor in the Raspberry Pi 4. So let's just quickly walk through this. And you know, obviously, this is the advantage of using a library is there's a lot more sophisticated and multi-platform support for this. So let's kind of dive quickly under the covers. So BCM2835 initializes all the kind of peripheral addresses and so on and so forth, but just quickly diving into that to see what's going on there, you can see that basically it's interrogating this part of the sort of device tree to figure out where the peripheral base is. So rather than hard coding it as I did in the other example, and that hard coding will work fine if you're using a Raspberry Pi 4, but if you're on a 3 or 3B or whatever, those addresses are going to be different. So that's what kind of this piece of code figures out here, is what is the peripheral base. And then it goes through the same process of opening up devmem. It checks here to see if you're root or not, because if you're not root, there's no point trying to open up devmem. And then there's basically setting up the base addresses for all the peripherals here, and you can see there's some hash defines here for each one of those. So the GPIO base is 200,000 hex, as we saw before. BSC1 base, that's actually where we'll be going for I2C here. There's actually 2 I2C addresses here, BSC0 and BSC1, and this is the one that is used on the Pi 4 for GPIO pins 2 and 3. So that's basically the initialization there. You can see there's a pile of code associated where, and this code even has support for dev GPIO mem. Now the interesting thing with dev GPIO mem is that is only for the GPIO pins. There is no SPI and I2C support, I believe, if you open dev GPIO mem. So let's get back to the code and see what's going on here. So after the initialization call, which sets up all the peripheral base addresses and so on and so forth, there's this call to I2C begin, and again diving under the covers there. All this is really doing is, if you recall that those alternate functions on the pins, well, this is basically saying for pins 3 and 5. So this is actually header pin numbers, not GPIO pin numbers, but that basically says for pins 3 and 5, I want you to use alternate function 0, and alternate function 0 for those pins happens to be I2C. So that sets that up. And then the next thing you need to do is set the address of the I2C device itself. And as I mentioned before, if you ground the ADRA pin on the ADS1115, that results in an address of 48 there. And then finally, setting the baud rate. Just sort of peeking under the covers of that, though, just to check out what's going on there. They're setting that address. Again, it's the same sort of thing. All we're doing there is poking values into the specific register. So in this case, it's peripheral BSC1 and register BSC-A. And if we go back to the manual, you'll be able to see that. There's register A there. And you can see there that that register is specifically for setting the device address. Obviously, that's the great thing about having a library, is all that sort of bit twiddling and understanding the magic values is abstracted from you. It's definitely good to know nonetheless. And then the final part is basically I took this code from the Arduino ADS1115 code here. Programming I2C is very straightforward. So basically what this does is sets up the configures the ADS1115. Here we're configuring it in single shot mode. We've got we're using the single channel A0, and we fire off that configuration, and then we wait for the conversion to complete and then get the results. And you can see here actually writing and reading to the register is a simple matter of using this BCM2811 I2C write and I2C read functions here. So here's the buffer 0 contains the register we want to write to, and then there is a 16-bit value that we're sending off when we write. And then on the read, we're just writing off the a single register, and the register for reading is just 0. And then we read a 16-bit value on the return. So the ADS1115 is a 12-bit ADC, so obviously 4 of those bits aren't meaningful, but we get that value back from the ADS1115 right there. So like I said, all this code is in the GitHub repo, so let's get on to actually seeing it running. And again, as I mentioned before, just pan down to the carefully pan down to the board itself here. All I've got is this pot connected up to 3.3 volts, and then off the center tap of the pot that goes straight to A0 on the ADS1115. So as I turn that pot, I will get different readings, or at least I should get different readings. So let's go and check that out. Bear with me, I've just got to move this terminal up a little bit. So I'll run that by sudo I2C, and you can see it's reading that there, and as I adjust the pot, that value is going up, and as I decrease the pot, decrease the voltage, that value goes down. Now, this can read quite quickly. I've got a delay in there of, let me just show you the delay there. I've got a delay in there of 200 milliseconds, but without that there, well, let's just do that. Let's see what that looks like without that there. Let me just make this guy now. Oh, bear with me. I'm all thumbs this morning. So let me just build that. Go back to the terminal. You can see there it's reading much more quickly now. So that's my I2C example there. As you can see from using the library, it becomes very straightforward, and it's very similar to the libraries that you would find, say, on the Arduino. So what I'll move on to next is an SPI example, again using the BCM2811 libraries. And I'll be using as the device there that SPI driven LED bank that I had used for the GPIO for my clock earlier. So anyway, that's coming right up. Okay, so let's move right along to the next example, and this is, in this case, this is SPI with the MAX 7219 IC that drives this 8-digit display here. So just going over the electrical connections again, connecting VCC to 3.3 volts, ground to ground, and then the three SPI pins that we're connecting here to data in. That comes from GPIO 10, which is header pin 19 or MOSI. And then the chip select comes from GPIO 8, which is header pin 24. And that is that's referred to as CE0, chip enable 0. There's actually another one, chip enable 1. So you got 2 pins to use there for chip select. And then finally, there's the clock there, which comes from GPIO 11, header pin 23, and that's also referred to as S clock. And as you can see over to the left here, we've got those connections coming in there from the appropriate pins on the ARPO. You actually can't see that. Let me move over a little bit. So here's those that cluster of SPI pins, and then here's VCC and ground. So let's dive into the code right now. We'll see how to drive SPI. Okay, so here we are in the code here, and you can say the initialization's the same as before, setting up the addresses of the peripherals and so on and so forth. We then move into SPI begin, and that piece of code, first thing it does is it sets the alternate functions for each of the pins involved here. And again, these are header pin numbers, not GPIO pin numbers. But you can see it sets alternate function 0 for the 2 chip enable pins, and then for MISO, MOSI, and the SPI clock. So once it has done that, basically the next step is to get the address of the SPI control register, and that's this guy right here. Now you can see everything is divided by 4, and the reason for that is PADRA is actually a uint32T, which has a size of 4. So when you're doing pointer arithmetic with this, it'll every +1 will actually add 4 to the pointer. So moving back to the SPI code again, you can see here it sets a series of values that control how SPI works. And the first one's interesting, this MSB first. Now, the MAX 7219 does happen to be most significant bit first, so the BCM2835 and 2711 don't actually have a LSB mode on SPI. You have to do the bit shifting yourself, and that is embedded in this library here. It then goes to set the data mode, the clock divider. Clock divider is important. This basically determines the frequency of the S clock, and basically it takes the clock frequency in the RPI and then divides it by this number. So the higher this number, the lower the SPI clock frequency. And then the final one is to set which SPI interface that you're going to use, and then chip select polarity. The general standard is you would have on a low voltage the chip is enabled, but there's a capability in here to set high if you need. So before we move on to the demo, let's just have a quick look at this write function. Here it is up here, and basically it accepts a register and data and then calls the SPI write number of bytes function with those 2 bytes there. So pretty straightforward stuff. And then the actual commands that I'm sending through SPI, these are pretty much the same as I did in my earlier video on the MAX 7219 as part of the GPS clock. So basically all I'm doing here is filling the register values here, and then I've got a loop here which basically displays all the characters in there, and just iterates varying the brightness from minimum to maximum. So that's basically the code in a nutshell. Let me just get this running so you can see that. Bear with me. Okay, so I'll just pan down to the board here, and we'll just fire that off. Again, I'm running this with the sudo function because this is privileged access. Let me just zoom out a little bit for you, so you can see that running, and fire that off now, and you can see that it starts with the test, and then it basically iterates through all the characters, slowly increasing the brightness of the LED. So that's that simple test there. So as you can see, using the library, it becomes pretty straightforward to drive these, and in fact, using the library is very similar to the way you would do this with Arduino. So basically, for my next little sample, I'm going to use the GPS GPS receiver that I used in the other one, and the final demo will be how to read from serial. I won't do a write here, but how to read from serial. The Ubuntu is pretty straightforward on the setup. There are some things you have to do on Pi to set this up, so I'll go through that quickly, and then we'll do the GPS demo. Okay, so moving on to Serial, which is probably one of the most straightforward examples here. So you can see Serial is exposed, or the mini UART's exposed on GPIO pins 14 and 15. So TX is from the Pi to the serial device. RX is from the serial device to the Pi. So what I've got that set up right here with the GPS, the QRP Labs GPS, which is off to the right there. So this yellow wire is the TX from the QRP Labs GPS receiver, and then that goes off to pin 15, GPIO pin 15 on the Pi. So that's the electrical setup. As I said, pretty straightforward. There's a couple of things that you do need to do on your Pi, at least if you're running Raspbian. And let me just quickly walk through those so that you can see that. So what you basically need to do is go into Raspberry config, and then you need to go into interface options. And this is to enable the default behavior of those ports is it's a command shell. So it's used to sort of remotely log in over serial. But if you want to use it as a serial device, go in here into serial port, and then there's two options here. Would you like a login shell to be accessed over serial? You want no there. And then the second one is, would you like the serial port hardware to be enabled? And you put yes there. So once you do that, get our Raspberry config. I've already done this, but you would need to reboot at this point. Okay, so once you've done that, reading from the serial device is relatively straightforward. It's very straightforward if you happen to have Python and the serial library. So I'll demo that first, and then I'll demo the same thing with some C code. But as you can see here, you just set up the serial device, and that happens to be on dev TTY S0, baud rate 9600, and then this is pretty much the default settings. Timeout is the timeout in milliseconds from reading from the port. And all I'm doing here is reading serial over and over again and just displaying the characters. So let's see that in action. Bear with me, let me just run read gps.py. And there you can see, as we did before, the messages from the GPS device over serial. Now it hasn't synced up yet, so there's no latitude and longitude there, but those messages are coming from the serial device. So what I'll do now is I'll do the same in C. Now the BCM2835 library doesn't have serial, but WiringPi does. So the example I'll be showing you would be using the WiringPi. So that's coming right up. Okay, then here's the equivalent C code using the WiringPi and WiringPi serial, wiring serial. And as you can see, it's very straightforward. At least it's very straightforward to use the library. You just simply open the device, dev ttys0. The baud rate's 9600, and that'll vary depending on from receiver to receiver. And then it's just iterating here, calling serial.getchar, and serial.getchar will return a -1 if there's a timeout reading. But there's always data coming through on the GPS, so that's probably not likely to happen. So anyway, let's run that so we can see the output. And just like the Python example, you can see there that there's the data coming from the GPS device. So anyway, that's probably a wrap for this video. I was interested in this topic of doing GPIO on my Pi, so I thought it'd be worth sharing kind of the learnings I'd gone through. As I said, one of the things I really want to do, and I'll probably do a follow-up video on this if I ever get to figure it out, is actually do I2S from the Pi using that PMod board that I'd done before. So hopefully I'll get to figure that out, and when and if I do, I'll certainly share it with you. That's all for now.